Alright, so this is a video tutorial on the second example for series solutions to ordinary differential equations. We are given y prime plus y equal to 0, and we're given y naught is equal to 2. So this is another boundary value problem. And the first step, as always, is to make sure the coefficients are 1. All of the examples have this because it's just easy to write it that way. One of the ones on the homework does not, so just make sure to check that. But the next thing we're going to do is write all of these terms on the left side of the equation as infinite series. So doing so, this is just y prime, this is the first derivative. So we have the sum from n equal 1 to infinity of c sub n times x to the n minus 1. And we just have y on its own, which is really easy. That's exactly what we want to see, because it makes writing the power series very easy. And then this is, of course, all equal to 0. We're not going to worry about the boundary condition yet. We're just going to find a solution first and then deal with it, because we'll deal with the implications later. But just like the last example, I want the starting index for each of the sums to be the same, and I want the powers on the variable, in this case we only have 1 and it's x, to be the same. So using the exact same trick as last time, I'm just going to subtract 1 here and add 1 to n every time I see an n inside of the first show. So if we go ahead and write that out, that's too high. Go ahead and write that out. We're just going to have n equals 0 to infinity. I'm going to do this in one step. C sub n plus 1 times n plus 1 times x to the n, right? Because negative 1 plus 1 is just n, just arithmetic there. And then the second series, does not change. And that is still all equal to 0. So I'm going to write this as a single infinite series, and I'm going to pull out the x to the nth power in the same step. So this is all still equal to 0. And in order for this statement to be true, the implication is that everything inside the sum here has to be equal to 0. Let's rewrite that. And we can use, just like last time, we can find the recurrence relation. A recurrence relation looks very, very similar. I'm not going to box it to last time, and that's because it's a very similar differential equation we're given. And just like last time, we're just going to test some values to see what the pattern is. It should be very apparent at this point because we did one just like it a second ago, but I'm going to take some liberties and draw the table anyway. Right? So when n is 0, we have c1 is equal to negative c0 over just 1, right? We're going to have c2 equals negative c1 over 2. But we found c1 up here, so this is just negative 1 over 2 times negative c0 over 1, right? c3 down here, negative c2 over 3, but again we just found c2, so that's negative 1 times 3 times negative 1 times over 2, times negative c0 over 1. And again, we see that there's definitely something factorially going on in the denominators of these terms. We also see that the negative sign is carrying, so just like before, we just continue the pattern. So obviously, I've been saying it a bunch, kind of spoiled it. The pattern's very, very, very similar. So ignoring the boundary value for now, we can say that some solution is going to be a multiple of this power series equals 0 to infinity of negative 1 to the n over n factorial times x to the n. This is in power series form. However, going back to the boundary value condition we're given, this is not the solution, because we're given y of 0, or y naught is 2. And for reasons which the homework will sort of imply, in order to reflect this boundary value condition, or this boundary condition in the problem, we have to put a 2 in front. And this is, as it turns out, sort of like a type of a very important function that comes up everywhere, and this is what it would look like, and that's the first question on the homework. So I'm going to want to represent this a little bit more compactly. I can say that y is the infinite series from n equal 0 to infinity of 2 times negative x to the n over n factorial. And that is the solution to this boundary value problem, which I believe was explicitly called a boundary value problem in the presentation.